For this video, we're simply going to talk about vertical, horizontal, and oblique asymptotes of a rational function. And remember, a rational function means it is in the form of a fraction, a numerator and a denominator. So we're just going to look at basically some functions. I'm going to look at the ones they gave us in the book, and we're going to look for vertical asymptotes first. So we're going to look at some function x over x squared minus 4. And basically all we're doing for vertical, it's very simple, and you've been doing this several times, is we're going to find out what the denominator can't be. So if you factor the denominator for this one, we know for our domain, let's look at our domain. Our domain is x, such that x can be all real numbers, but it can't be plus or minus 2. Because if you put plus 2 or minus 2 in here, you'll get a 0. That means we have a vertical asymptotes at the lines x equals plus or minus 2. So just notice that this should match here. So if you can find the domain, you can find the vertical asymptote. And again, that just means the vertical asymptote just means that it won't cross at 2 and negative 2 when you draw the graph, which I don't think we're drawing in this section. So, alright, so let's go and do another one. Another thing we need to remember is that when you do find your vertical asymptotes, that your rational needs to be in lowest terms. So this one, we can tell it's already in lowest terms. I'm going to go ahead and do my domain, which means it's all reals. However, x cannot be what? 1. That means we have a vertical asymptote at x equals 1. So the graph can't cross there. Now let's look at another one. Let's look at h of x equals x squared over x squared plus 1. Okay, so since there is nothing in the domain to make this real number-wise that can make the denominator 0, for the vertical asymptotes, we have none. Okay? And then we have, let's do one where we have to reduce. We have one that is x squared minus 9. We'll call over x squared plus 4x minus 21. Now when you factor this, you're going to get x minus 3 or x plus 3. Oh, my thing's not working. Alright, plus 3 over x plus 7 over x minus 3. Now for the domain, we know that x cannot be it's all real numbers, but x cannot be 3 and x cannot be negative 7. Okay? So, now, if we reduce this equation, it means I can cross out these two. This is called here the depressed equation. And from the depressed equation is where you get your vertical asymptote. So in this case, the vertical asymptote is x cannot be, or x is negative 7. Now basically what I want to do with this video is to kind of go over generally the horizontal and oblique asymptotes that are coming up. When you read it in the book, it can be kind of confusing. And we're going to go over limits in class and talk about it as a class. But as far as horizontal asymptotes, what you need to know is, first of all, you can have vertical and horizontal asymptotes. So we always look for the vertical just by looking at the denominator. What makes the denominator 0? However, for the horizontals, you're looking at two cases. You're looking at a case where you have a numerator. For example, this problem here. In which the degree of the numerator is smaller than the degree of the denominator. So 1 is less than 2. That means this is called a proper rational, and we're going to have a horizontal asymptote at y equals 0. Horizontal meaning the line that goes horizontally. So that's my horizontal asymptote. Now, as far as limits go, let's just look at something. Let's just say we have 1 over 4x. Now, if I put big numbers in here for x, so if I let, and the way they do this is that they're going to say the limit as x approaches infinity. So the bigger this number gets, for example, if x was 1,000,000, then you'd have 1 over 4,000,000. We know that that is very close to 0. Okay? If this was a billion, so we have 1 over, a lot of zeros. Let's just put a lot of zeros here. It's 400 million here. If I did that, this number gets really close to 0 without getting to 0. So that's why this is called the horizontal asymptote at y equals 0. What if I had x over x squared? Again, the degree in the numerator is smaller than the degree in the denominator. So if I take the limit, and as x gets bigger and bigger, the same thing's going to happen. Because if I plug in 2 here, we're going to get what? We're going to get 2/4. If I plug in 3 here, we get 3/9. If I plug in 4, we're going to get 4 over 16. This number gets closer and closer, which is really 1/4, right? This gets closer and closer to 0. So that's why they're saying if the degree in the numerator is smaller than the degree in the denominator, then you have a horizontal asymptote at y equals 0. And again, we'll talk about this more in class. Now let's look at where the degree is the same. Let me see if I can find one in the book where the degree is the same. So let's look at this one. R of x equals 3x over x plus 4. Now, the degree in the numerator is the same as the degree in the denominator. So what they want you to do is they want you just to take the lead coefficients and divide them. So I'm going to divide this 3 to the x to the first over x, and that equals 3. So your horizontal asymptote is y equals 3. Let me pick another one. What if I had, let's do another one. Let me just make something up. If I had r to the x equals 10x plus 5 over 5x plus 1. Okay? The degrees are the same. And so if I take these two here and divide it, you get 10x over 5x. That cancels, so my horizontal asymptote would be y equals 2, because 10 divided by 5 is 2. Now what's happening here is they're taking limits again. So they're taking big numbers, and if I take the limit as x gets bigger and bigger, and let's let it be 1,000,000, say. So really what I'll have here is, on the top, 1,000,000 times 3 is 3,000,000. And on the bottom, what I'm going to have is 1,000,000 and 4. When you look at this 4 here, it's really insignificant. Very insignificant. So when you have this little 4, it's kind of like a cast off. And if you disregard it and you divide this, we're going to get closer and closer to 3. And that's why the horizontal asymptote would be y equals 3. Same thing for this one. If I take the limit of this as x approaches a huge number, then I would get 10,000,000 and 5 over 5,000,000 and 1. Again, these two numbers here are pretty insignificant, because when you take huge numbers, when you divide this out, it's going to get closer and closer to 2, which is what we have here. And that's what the horizontal asymptote would be for that. Okay? Now the other one we have is called the oblique asymptotes. They're or some teachers call them slant asymptotes. And that's when the degree in the numerator is larger than the degree in the denominator. And the only one I'm going to go over is when it's 1 off. So I'm going to look at, let's see, I'll look at h of x equals x cubed minus 8 over x squared minus 5x plus 6. And that one might be a little too complicated for this, but basically, it is going to be a little too complicated for this. But anyway, I'm going to factor this as x minus 2 times x squared plus x plus 2. This would be AB, so that's 2x plus 2. Alright, over x minus 2 times x minus 3. Alright, in this case, we're going to cancel this here. We'll talk about this thing here that we're canceling next section. And what I have is a division problem here, and the degree in the numerator is 1 higher than the degree in the denominator. That means we're going to get a linear slant asymptote. We're going to get a linear line that this is going to our graph is going to reflect over. And what you're going to do is divide. Now we do have a vertical asymptote at x equals 3. So we do have a vertical asymptote at x equals 3. But that has something to do with our oblique asymptote. So all you're going to do is divide. Alright? And we're going to get x squared plus 2x plus 4. And I apologize for doing this wrong, but this should be a 4. Alright, and then we're going to just do long division. So you're going to say what times x gives you x squared, and that's x. And you get x. And you multiply this, and you get x squared minus 3x. You subtract, and you're going to get 5x, and bring down the 4 plus 4. So this is going to be plus 5. 5 times x is 5x minus 15. And basically you're done. This is going to give you 24 remainder. And again, we'll talk more about this in class, but when you're taking limits of this little piece here, this remainder business, is not going to affect it when you take limits. So our our oblique asymptote is y equals x plus 5. Okay? And that's what we're going to be doing in class. Let me see if I can find another one. Let's do this one. We have r the x equals 3x to the 4th plus 4 over x cubed plus 3x. Now, I'm going to go ahead and factor out the denominator and see what happens. I'm going to factor out an x, and we get x squared plus 3. That doesn't help me, except it tells me that x can't be 0. So I have a vertical asymptote at x equals 0. And so we get 3x to the 4th plus 4. Since the degree in the numerator is 1 higher than the degree in the denominator, that means we're going to have to do long division. Now, since we're doing long division, I'm not going to use this one. I just did this to get the vertical asymptote. I'm going to use this one right here. And I'm going to go ahead and write it out. So it's x cubed and plus 0x squared plus 3x plus 0, if you will. I don't even think we need that, so I'm going to just leave it like that. Divides 3x to the 4th plus 0x cubed plus 0x squared plus 0x plus 4. And basically, we are going to get a linear equation. Once we have the linear equation, we can stop, because that's our slant asymptote or our oblique asymptote. And you just simply divide here, and you're going to get 3x to the 4th plus 0x cubed plus 9x squared. And we're going to subtract, and here we get negative 9x squared plus 0x plus 4. Now at this point, we can't divide anymore because we already started with 3. So we're done basically. We don't have to do anything more. And our oblique asymptote is the line y equals 3x. So we're going to have some equation where it's going to reflect, it's going to do something like this. Something that's going to reflect over this line. And that is all. We'll definitely talk more about limits in class so you can get more of a conceptual understanding. But just looking at the rules, and I suggest you look at the green boxes and look at those as well.